Okay, everyone, welcome back. Good morning. Let's have a look at our calendar here. It is the 10th of September. Okay, so we just finished exam one. I haven't received those yet from the testing center, so I'll probably get those in the next day or two, get them graded and back to you with a little luck by the end of the week. But definitely, if not by Friday, I'll have them on Monday. Okay, so we're ready to switch gears here. We're done with the first two chapters, and we're going to move into chapter three today. We're still working with categorical data here, mostly. So a couple things. Today is the last drop day, so you can drop today with 100% refund. I don't want any of you guys to drop, but it's just something to consider, I suppose. So that's today, and then uh, we've got the project, right? So the first part of the project, I think it's due in about a week or so. Um, so please get started with that if you haven't. Do you guys have any questions for me as we get going here with our new chapter? Nothing? Okay. Well, let me know if anything does come to mind as we get going here. Just let me know. Okay. So we're in chapter three. We're still mostly working with categorical data, and we're going to apply the normal distribution here to categorical data. Right? Yes, the homeworks do lock at the time of the midterms. And the reason I do that, I used to just leave homeworks open all semester and just let students work on them. What I found is that uh, for the conscientious students, it didn't make any difference really. But for students who have a little harder time staying on track, I just felt like they started to get further behind. So I like to have a hard deadline on the homework. And so, yeah, at the time of the midterms, it tends to, at the time of the midterms, it'll close. I will open the assignments at the last week of the semester just to, if you've got like an assignment or two that you need to finish up. So, yeah, the assignments do lock. Um, what should part one of the project look like? Let's see. Did I talk to you guys about the project? I think I did a little bit, right? About the countries, the tuberculosis data, right? So when you mean what does it look like? Do you mean like the format I wanted in? I'd like it to be typed, um, to have nice screenshots of the applet. Is that what you mean, Brock? Or were you looking for more instruction about the whole project? Oh, okay. Yeah. So there are, yeah, let me just remind you guys of where to go for the general instructions here for part one. So over in the modules at the end of chapter two, we have that TD part one. Okay, so yeah, it's due in a couple of days. I'm pretty flexible in the due dates for the project. So, try to get it done by the 12th, but if you need more time, you can have it. So yeah, just as a reminder, you're going to get a random sample of 10 countries that participate in the World Health Organization, and you're getting data on their tuberculosis treatment that they do. Okay, so it's got to be a random selection. And so I recommended that you do a simple random sample using the GeoGebra random number generator, if you remember. Okay, so yeah, so you have your 10 countries, and then for each country, you'll get the TB incidence, the success rate, and the cohort size. That data set you'll use for all four parts of the project. So you need to get this part right. If this part is wrong, then the whole project could be compromised. Okay, so once you have that, then you have part C, D, and in these two parts of the project, you're looking at a bar chart. Okay, so you're gonna look at a bar chart, and then you're going to do a hypothesis test using the Rossmann chance applet that we've looked at a couple of times in class. Okay, so yeah, you want to type that up, make it look nice, like a professional, project or report, and then you'll submit that on Canvas. If you want to work on it with somebody else, you can. If you want to work on it separately, you can do that too. Okay. All right. So hopefully that answers your question, Brock. If not, we can feel free to talk with me after class about it. So let's get going with chapter 3. 3.1 is a very brief section. It's just one page, and there's not really any problems to work on. It's really just setting us up for understanding this central limit theorem and for getting us thinking about the normal distribution. Okay, so uh, so it says the central limit theorem for proportions, the sample proportion will approximately follow a bell-shaped curve. Okay, so it looks like, you know, an old-fashioned bell, right? And we call that curve the normal distribution if if the observations are independent and if the sample size is large enough. So what on earth is that saying? Well, we've actually already worked with this a little bit. Okay, do you guys remember the null distribution that we built with our applet? I believe right before our exam, I guess it was about a week ago, we went through this problem here. We were looking at this physical therapist. And so for this particular treatment, there's a 70% success rate. So that's just sort of a national level. And so the idea is as long as you're about 70%, then you're competent, right, as a physical therapist for this particular treatment. So if you go above 70%, then you're excellent. If you go below 70% too far, then you're incompetent, right? Or something's going on, right? And so there's an online review that says that this therapist is performing below 70%, right? So the null and the alternative here, the skeptic's hypothesis is that this physical therapist is the same as the national average, right? The 70%. This online review is saying that this physical therapist is below 70%. Okay, so to test that, we have a sample. Okay, so 60 people, we have a random sample of 60 people who got this treatment, and 31 were successful, right? So we already did this last week, but let's just go ahead and think about this again. So 31 divided by 60 would be the sample proportion of successes. So that's about 52%. Okay, so 52% is not 70%. It is indeed less than 70%, but is it convincing? Okay, so we can use the applet, right? So let's pull that applet out again and use it. Let's see, where did it go? Right here. Okay, so we go to the one proportion and we put in the null value of 0.7, and then we had a sample of size 60, right? And then so every time I hit the button here, we're going to get a random sample of 60, right? And so let's turn that off. Sorry, let me reset that. Okay, so every time I hit the button, we get, hold on, I don't know why it's doing that. Let me try it one more time. So 0.7. Okay, so every time I hit the button, it's going to give me, just ignore the graphic up at the top. Oh, okay, there we go. Hide those spinners, there we go. So every time I hit the button, right, we're getting a random sample of 60. And what it's doing is it's saying, well, if this physical therapist does have a 70% success rate, we're seeing, okay, well, you know, if we do it a trial of 60, you know, how likely is it that we would get how many successes? 31 or fewer successes, right? So we put in the 31 down here, and we go less than, and we start counting the number of times. By chance, we get something below 31, right? And it's starting to look like this physical therapist is doing something wrong, right? We haven't gotten a single one just by chance. Okay, so anyway, we concluded basically that something was going on with this physical therapist. Maybe his clients are ill. Maybe he's just working in a subpopulation that's more sick than the rest of the population. But the p-value here is very low, so we can probably reject the null. Okay, so that's what we're doing in chapter 2. What I want to focus in on in chapter 3 here is the null distribution itself. Okay, so let's get this up to kind of a normal size here. So let's do it 100 times. Okay, so now I'm up to about 100 rounds of 60, and we're starting to see the shape take place here with this null distribution. I'm also going to turn this into proportions. So this is our null, and so to make this go a little bit faster, I'm going to go to 100 rounds of 60, and so every time I hit the button, we're getting 100 new dots, right? And you can see that the null distribution is taking shape. It does start to look like a bell-shaped curve. Now, it's not a perfect bell-shaped curve. It's a little bit longer on the left than on the right. But that's what the central limit theorem is telling us. Okay, so if we go back to 3.1, it says, okay, if you have a small sample size, then it might not really look very bell-shaped. You might have some skew, you'll have some spaces between the columns, but as the sample sizes increase, as you go from, say, size 20 to size 100, notice that it does become a little bit more symmetric and the distance between the columns decreases. And then if we go up to 500, then it actually becomes quite symmetric and it's a very nice tight bell-shaped distribution. Okay, so what it's saying is that our null distribution becomes more and more like a bell-shaped normal distribution. We can see that here. So if we had done this, say instead of 60 clients, if we had done maybe 10 clients, a sample of 10, and we start drawing the distribution, we can see here, yeah, there's spaces between the columns and it's longer on the left. Okay, but if we do, say, samples of size 100 clients, do you see how the spaces between the columns decreases and we tend to start getting something that's more bell-shaped? So let's move up to size 500. Okay, so now every time I'm going to get 300 rounds of 500. And again, notice that those spaces between the columns decrease. And let me do lots of them here. Whoops. There we go. It just took the computer a second to do that many samples. Okay, so it really does start to become quite normally distributed. And if I turn on this normal approximation here, you can see that it's actually almost a perfect normal distribution. Okay, so that's what the central limit theorem tells us. It says the sampling distribution for p hat, which is the null distribution, will become more and more bell-shaped, and we call that the normal distribution. Okay, so what's the point? Well, the point is that since the null distribution, since the sampling distribution becomes this normal curve, then we can use the normal distribution. Okay, and that's what chapter 3 is all about. It's using the normal distribution. Okay, so the normal distribution is overwhelmingly the most common distribution in statistics. Okay, so there's lots of distributions in statistics. So if you've enjoyed this class and you want to take more stats classes, then you'll learn about all sorts of different distributions. You'll learn the t distribution, the chi-square distribution, the f distribution. The list goes on and on and on. Okay, but for sure, the most common one is this normal distribution. So what are its properties? That's what we want to study here in chapter 3. Well, first of all, it's symmetric. Okay, so if we look at this picture here, if you imagine putting a mirror down in the middle, the left side would be a mirror image of the right side. So that's what it means to be symmetric. It means the two sides are mirror images of each other. Secondly, it's unimodal. Uni means one, right? So uni means one. Mode means peak or largest value. Okay, so if you look at the normal distribution, it has one peak, and that peak is in the middle. Finally, the normal distribution is bell-shaped. So if you go out in the tails, it has this decreasing pattern here where it starts to approach, although it never quite touches the x-axis. So how does it help us? Well, we're going to study all the properties of this distribution, and then we'll be able to use that distribution to help us understand p hat and the sample proportion and the population proportion better. Okay. All right. So, so some other things about the normal distribution. To help us understand our position in a normal distribution, or actually any distribution, we can use what's called the percentile. Okay, so the percentile is the value where that percent of individuals are equal to or below it. Okay, so you might be familiar with percentiles already. So we use percentiles to help us measure people's heights and weights. So if you remember from when you were a child, you might remember that you went to the doctor and they would measure your height and they would say you are at the 50th percentile for height, or you're at the 80th percentile for height if you're tall, right? Or you're the 30th percentile if you're a little bit shorter. Yeah. So these are percentiles. Okay. And we can use them in all sorts of distributions, all sorts of different distributions. So for example, let's say we're looking at the distribution of IQ scores of honor roll graduates of a certain college. Okay. So the 85th percentile is 124. What does that mean? Okay, well, don't have a lot of space here, so I'll try to get this in there. So what it's saying is okay, there's some middle score for the IQ, but we don't know what that is here. What we're saying is that if you go out to 124, then 85% of the students are at or below 124. So that means 85% of the college's honor roll graduates have an IQ score equal to or lower than 124. Okay, so it's a way of explaining where somebody falls in their population, right? So we do that with all sorts of things: heights, weights. Are you taller than average? Are you shorter than average? Income, to make more money, less money, right? And so this number allows us to position somebody in their population. Okay, so if 85% are equal to or lower, then 15% are higher, right? 100% minus 85% equals 15%. So I want you guys to do this next exercise. Instead of IQ scores, we're talking about commute distances, right? So when you come to college, uh, you have to drive or what, you could walk or take a bike or a bus, right? But anyway, unless you live on campus, then you're going to have to travel some kind of distance. And if you live on campus, then you still travel a distance. You just travel a distance of 0, right? So what it's saying is that the 80th percentile of distances driven to commute to college is 12.4 miles. So I want you guys to interpret what that 80th percentile statement means. Okay, so just fill it in. It's very much like the last problem. Percentiles is usually quite easy to grasp, I think. And as soon as you do it, just tell me what those numbers are. If you could just put them in the chat or say it out loud. Somebody fill in the blanks for us here. Anybody, please? So what percent of the students drive blank and then blank percent drive? Okay, great. So Brock is saying 80%. So yeah, if it's the 80th percentile, then that's a longer than average commute typically, right? So great. Yep. So 80% drive up to or less than. Yeah, great. So yeah, you could say it in a number of different ways. So equal to or less than, something like that. Okay. So equal to or less than. So if 80% drive less than 12.4 miles, then that means 20% have a commute that's longer than 12.4 miles, right? So more or something like that, right? Good. So that's percentiles. It's great. We use it quite a lot. So, if you work in medicine or, you have a child and you've been taking them to the doctor, you've been seeing these percentiles a lot, right? But and it's great, but for doing math and for doing harder calculations, we have another way of positioning somebody in a population, okay, of understanding where somebody falls in their population. okay? And that's called the z-score. It's a little bit more sophisticated, and its uses are quite a bit broader than the percentile. It's got a formula. It's right here. In fact, this is our first time to actually look at our formula card for the semester. Okay, so let me show you that real quick while I'm thinking about it. So we do have a formula card. I didn't really talk about it before the first exam because it doesn't really apply to the first exam. All of the formulas on this formula card start in chapter 3 or later. So to find the formula card, you'll want to go to the home page. And then on the home page, it says formula cards. So click on there. There's a few documents here. Probably the one you'll want to use right now is this version 1 PDF. So you can download that. And I do recommend from this point on always having it downloaded and ready to go. Okay, so download it, print it off, and just have it at hand here. And so yeah, this is probably what you were expecting to see when you signed up for stats, right? Lots of formulas, and well, here they are. Stats does have a lot of formulas. Okay, and so the very first one on the sheet is this. It's the z-score. It's also called the standard normal score. Okay, so it says z equals x minus something minus over something, right? So have you guys seen those before? So x minus what's called mu divided by sigma. Okay, so that's the formula. So let's talk about these letters. Okay, so the Greeks were very prominent in the early history of mathematics. So a lot, so a lot of the notation we use kind of reflects that. So this is the Greek letter, and it's pronounced mu. Okay, and then this one here is also a Greek letter. It's called sigma. Okay, so what are those? Well, mu is the center of the population, and sigma is the spread in the population. Okay, so what does that mean? Well, some populations are more spread out than others. Okay, so some populations are very similar, um, and their spread or their average differences are smaller. Okay, and then in some populations though there's more spread, right? So there's more, it's just greater differences, right? So sigma is our measurement for how spread out a population is. Mu is the measure of the center or the average, okay, or the mean, okay? And this diagram here gives us a nice way of thinking about center and spread. Okay, so mu is the center. It's also the mean when we're in a normal distribution. Okay, so that part's easy. So we have mu in the middle, it's under the peak. And then look how spread out this distribution is. Okay, so if we start here in the middle and we go over to the side of the graph, that's it. There's a distance there, and that distance is sigma. Okay, so we have to understand this other thing called the inflection point. Okay, so to understand sigma, we have to understand the inflection point. So let's talk about that, and then we'll define sigma using the inflection point. Okay, so I kind of like to use the example of a roller coaster. Okay, so let's imagine you're on a roller coaster and you're up here at the top of the hill on the roller coaster, right? So you're up at the top and it's actually flat, and then you go over the top of the hill, right? What happens? Well, at first it's going kind of slow, right? It's actually not very steep up there, okay? But as you go further, it starts to get steep, right? So it's getting steeper and steeper and steeper. But then later it starts to flatten out, right? So it's getting flatter and flatter and flatter, right? So over here it's getting steeper every time you move a little bit to the right, it gets steeper. But down over here, it's getting flatter, right? So at some point, it has to switch from going steeper, steeper, steeper to flatter, flatter, flatter. Where did it switch? That's known as the inflection point. Okay, so the inflection point, every normal distribution has an inflection point. Okay, and there's actually two of them. It's on both sides of the center, and since it's symmetrical, it's the same distance on the other side. The inflection point again is that point where the graph goes from steeper, steeper to flatter, flatter. Okay, and so you can kind of see it with your eyes, right? If you look at it carefully, you can just kind of tell where that point occurs, more or less, right? So that distance from the center to the inflection point measures how spread out the distribution is. Okay, and we call that measurement sigma. Okay, so sigma is how spread out it is. Let me give you an example of two distributions that have more or less spread. Okay, so if you're thinking about income distribution, okay, income is famously, very spread out, right? I mean, there's some people who make huge amounts of money, right? And some people who make much less money, right? So we have the center, and there's quite a lot of spread there. I think you just imagine, right, that there's just so much spread there because you've got people making tons of money and you have people making very little money. There's more spread in that population. Okay, so you can imagine a society like in the US where there's just tons of variation there in income levels. But if you take another society, lots of other countries will have less spread in incomes, for example, right? They'll just have a more kind of uh, you know uh, egalitarian, I guess you could call it, distribution. Does that make sense? So not every society would have the same spread. So that sigma value can be more or less depending on how spread out uh, that value is. Does that make sense? So let's use an example here. I think it might just be best if we jump into an example. How can we use the z-score, sigma, and mu? Okay, so let's say we have a biology course and a statistics course. Okay, so it's not hard to imagine that. You guys are all actually in a stats course, right? So let's imagine that you're also in a biology course. Probably some of you are. Right? So at the end of the semester, you have a final exam in biology and you have a final exam in stats. For the biology course midterm final exam score, the average is 79, but not everybody gets the same score, right? So some people have a higher score, some people have a lower score. So there's some spread in that distribution, right? So we measure the spread with standard deviation. Okay, so I think I might have forgotten to use those words. Sigma is the standard deviation. Okay, sorry. So standard deviation is sigma, and it's our measure of spread. The mean is mu, and it's 79. Okay, so that's for your biology course. So the mean is 79, standard deviation is 5. For your stats course, the average on the final is actually a little bit higher. So maybe the stats exam is a little bit easier than the biology exam. Okay, so the mean for that course is 82, and the spread or the standard deviation is a little bit higher. Okay, so the distribution of final exam scores is a little bit more spread out. You've got higher scores and you've got lower scores, right? Okay, so let's say you did better than average in both classes. You did well. You got an 86 in your biology exam. You got a 91 on your stats final. How many standard deviations above the mean were you in each course? Okay, well, that's what the z-score measures. Okay, if we take x minus mu and we divide by sigma, that tells you how many standard deviations or sigmas you are from the mean. Okay, and what it allows us to do is to compare your score across two different distributions, right? Two different populations. There's the population of stats scores, there's the population of biology scores. They're different exams, but by computing a z-score for both of your exams, you can actually compare to see which course you did better in. What do I mean? Well, let's do this and then you'll see, I think. So x is the observed or measured score. Okay, and that's your 86. You got an 86 on your biology exam. Okay, mu is the mean, it's the middle, and for biology, the mean was 79. Okay, then The sigma, or the standard deviation, or the spread for biology was 5. So your z-score, which is your number of standard deviations away from the mean, is going to be 86 minus 79 divided by 5. Okay, so it's calculator work. It's very easy to calculate that. So we just go 86 minus 79. Make sure you hit the enter there, or use parentheses. So it's 7 divided by 5, giving us 1.4. Okay, so then if we take the absolute value of that, it's also 1.4, and that tells you you got 1.4 standard deviations above the class mean. Okay, so why do we like that? Well, I can do the same thing for your stats score, and then we can see relatively which test you did better on. Okay, great. Sarai got the same answer there. Perfect. Good. So let's do the stats one. So you got a 91 on stats. The mean for stats is a little bit higher, but the standard deviation was more. Okay, so we go x 91 minus 82 divided by 7. So that's going to be 9 divided by 7, which is 1.29. Okay, so the absolute value of 1.29 is 1.29, which means you scored 1.29 standard deviations above. It's above because it's positive. Okay, so how many standard deviations from the mean was your biology score? Well, it was 1.4. How many standard deviations from the mean was your stats score? 1.29. Okay, so yeah, your absolute score in stats was a 91, and yeah, that is higher than 86. But it kind of appears that the biology test was harder, right? Um, so by using the z-score, we can say, well, actually in biology, you scored relatively higher than stats because compared to your peers, you just did, better than relative to your peers in biology than you did in stats. Does that make sense? So it's a really nice way of comparing across different populations, right? So again, it's a measure of, how well, or where you are, what your position is in your population, and that population can be just about anything: height, weight, blood pressure, income, you name it. Okay, so you guys try one. Now you're looking at your friend, right? So you got a buddy who took the same stats class with you and the same biology class with you. Maybe you're both nursing students or something. But your friend didn't do quite as well. In fact, they did below average in biology. They got a 73 in biology. They did below average in stats. They got a 74 on the stats final. Okay. So relative to the students in the class, on which exam did this student do worse? So what you're going to do is you're going to calculate the z-score for the biology class for your friend, and then you're going to do the z-score for the stats exam for your friend. Okay. So I'll go quiet for about 3 or 4 minutes and let you guys do that. Use that same z-score formula, and you should get a negative z-score. So resist the urge to reverse x and mu and always get a positive score. Some z-scores are going to be negative. Okay, so that's fine. The negative, if it is truly negative, that gives us information as well. So we don't want to lose that information. So anyway, I'm going to be quiet for a couple minutes. As soon as you get the z-score for biology, put it in the chat. As soon as you get the z-score for stats, put that in the chat, and we'll keep going here. Oh, yes, Polly, that's right. Yeah, we still need the information from above. Yeah, so it's the same mean and standard deviation for both biology and stats. Let me write that down here. So yeah, we still have the same mu for biology. I'll write that here. So let's see here. That would be 79, sigma equals 5, and then for stats, the mean was a little bit higher, and there was more variation. Okay, so there you go. You'll need to use those numbers again. Anybody have a z-score for us? Maybe either biology or stats? Let's see here. So your friend got a 73 in biology. The average is 79. So they got below average. Great. Let's see here. Polly, I agree with the bio score. The stats looks a little bit off to me. So let's see. So your friend got 6 points below the average, and the standard deviation is 5. So they got, more than one standard deviation below average. Okay. So that's coming in at negative 1.2. Okay. So if we take the absolute value of negative 1.2, we get 1.2. The negative sign tells us that the friend is below the class mean, right? So they got 1.2 standard deviations below the class mean. Okay. And so just as an aside, these z-scores are also commonly used in medicine. So percentiles are used quite a lot, but they also will use z-scores. So keep an eye out for that next time you go to the doctor and you have some measurements done. Very often they'll present a z-score in there in the documents. So okay, so they did below average on the biology, and then for stats, yes, it's also negative. It's also it is negative 1.14. Okay, so how do we do that? Well, we take the observed score 74 minus the mean, which is 82, divide by 7, and it's negative 1.14. Okay, so if we take the absolute value of that, that's 1.14, and that tells us how many standard deviations away they are. Because the z-score is negative, we know that they are below the class mean. So 73 is lower than 74. Okay, so in the absolute sense, they did worse in biology than in stats. And then if we compare relative to the two populations using the z-score, we see that also in a relative sense they did worse in biology, right? So the students scored lower in the biology test relative to the rest of the students because it was further below the mean. So both in an absolute and a relative sense, they did worse in biology than in stats. Okay, good. So what do you guys think here? The z-score, very, very commonly used. In fact, you never really get away from z-score from now on. Pretty much it's hard, especially for this class. It's just sort of always behind the scenes. Sometimes it's front and center. It's everywhere in stats. Okay, because it's the normal distribution. Okay, so what we're going to do now is we're going to take that z-score and we're going to learn how to find percentiles. Okay, so we've seen percentiles, but how do we calculate percentiles? Well, if you have a normal distribution and a z-score, it's actually quite easy to calculate percentiles. Okay, so any questions about that example? Okay, so what we're going to do now is we're going to standardize. What does that mean? Well, it just means that we're going to take everybody in the population and we're going to calculate a z-score for them. Okay, so let's think about maybe heights. Okay, so everybody has a height. Okay, and that means we can calculate a z-score for everybody, right? So maybe my z-score, I'm a little bit shorter than average, so my z-score might be negative 1.2, right? Somebody else might be a little bit taller, their z-score might be 0.3, right? Somebody else might be average, their z-score is 0, but we all get a z-score, okay? So if we look at, let's imagine this might be the histogram of heights, right? So let's say it's normally distributed. So that average height there is in the middle, and there are some taller people, but it's less common, right? So the taller, the higher the height, the less common, it is, right? So it tends to decrease to 0. And the same for shorter heights, right? So that, the shorter the height that we're looking at, the less common it is, right? By the time you get down to like 4 or 3 feet, I mean, nobody, it's very rare to be that height, right? So it happens, but it's just not as common, right? So we have that peak that's decreasing, right? Um, so we all have a height, right? And then so if we calculate a z-score for everybody, and then we plot the z-scores, we actually get another normal distribution, but we call this distribution over here the standard normal distribution. Okay, so with the standard normal distribution, it's basically a distribution of z-scores. Okay, so again, just take any normal distribution and you start giving everybody their z-score. Okay, so you then take those z-scores and you make a plot from that. You get the standard normal distribution. The reason we like this is because it's sort of like the parent or foundational normal distribution. So it's kind of like the most basic fundamental normal distribution. And so with the standard normal, the mean is 0 and the standard deviation is 1. Okay, right? Why would the mean be 0? Well, if we're looking at a bunch of z-scores, what is a z-score of 0? It means you're right at the middle of the distribution, right? So So make sure you know that. That's an important fact. This standard normal distribution plays an incredibly important role in the theory of stats. Okay, so in the theory of distributions. So how does it help us? Well, let's look at an example here. We're looking at a soda can dispenser. So one of the uses for stats is quality control. Okay, so in, say, food production, these factories that are making beverages or they're making processed food, they're making lots of these products very quickly, right? So you might have thousands or, hundreds of thousands of products that you produce, in a short period of time, right? And you can't do quality control on every single item, right? You can't measure every single Snickers bar or every can of Coke, right? It's just it would become too expensive to do that. So you do samples, right? So anyway, long story short, a lot of statistical theory was developed for doing sampling for stuff like this. Okay, so we've got this soda can dispenser. It has a mean fill volume of 12 ounces, but you know how the world works, right? With these machines, the target might be 12, but if you have good enough, tools to measure the actual fill, you would find that usually it's actually probably a little bit off, right? It might be a little bit more than 12 ounces, might be a little bit less than 12 ounces. As long as it's close enough to 12, then nobody can tell and you're fine, right? So since not every can is exactly 12 ounces, there's a spread in the population, and we can measure that with the standard deviation. Okay, so what that's telling us basically is that mu is 12 and sigma is 0.12. So what proportion of cans have fewer than 11.9 ounces? Okay, so on the left we have the distribution of fill volume. Okay, so the mean is going to be 12, so we'll put that in. So we'll go mu 12. We have a line on the x-axis, and it's right under the peak of the normal distribution. Then we're going to go out to the inflection point. Okay, so you guys tell me when to stop. Where is that inflection point? So just say it out loud, somebody. I mean, we're going to slide down the curve. Where does it go from steeper, steeper to flatter, flatter? Somebody tell me when to stop. Oops, I think I missed it. Let's see here, maybe right there. Does that look right? Okay, so that's the inflection point. So if we go from the center to the inflection, so that's going to be 12 plus 0.12, that's 12.12. Okay, so the reason I'm doing this is because it gives me an idea of the layout of the population here. Okay, and likewise, over on the left, we have another inflection point. So let's see, that would be 12 minus 0.12. So that would be 11.88. Get in the habit of drawing the inflection point. It'll help you out. I promise. You'll just get better results. They'll look better. They'll make more sense. Yeah. Where do I know? Well, I don't know exactly where it is. I mean, because I'm just looking at the graph, but you know, intuitively, like, I mean, I think you could tell it's really flat here. It's really flat here. It's steeper here. And then so where does it get, you know, where does it go from steeper, steeper to flatter, flatter? So again, let me just try to turn that into a bit of an animation here for you. So again, you're up here at the top, you're going over to the right, it's getting steeper, 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 but down over here it's getting flatter and flatter and flatter. So where did that transition? To my eyes, it looks like about that point right there. Does that make sense, Polly? So it's not perfect, but it's pretty close to about that point. Does that make sense? Or no? That's called the inflection point. Okay. All right, and then just by symmetry, it appears that it would be about this that point right there. Okay, so what are we after here on this one? We're trying to figure out the proportion of cans that have fewer than 11.9. So let me get rid of some of this. Okay, so where's 11.9? 11.9 is actually very close to 11.88. Okay, in fact, it's probably indistinguishable, right? So maybe there, that will be 11.9. Okay, so let me get rid of that and replace it with 11.9. So why did I use that inflection point? Well, because I actually can get a pretty good ballpark estimate just by my graph now, right? What proportion of cans are going to have a fill below 11.9? So I shade that area. And what do you guys think? What is the proportion there that's shaded? What would you know, just kind of ballpark, would you say that's 80%? Would you say it's 50%? Would you say it's like 20%? Yeah, 25. Yeah, great. Yeah, I mean, that's about as good as you can do by ballpark, right? You know, by approximation, but that's good. It's nice to have an approximate idea, kind of a guesstimate, right? So yeah, I would say it's maybe 20, maybe 30. We'll go with 20% here. Okay, so if you forced me to guess, I would say maybe about 20% of the cans have fewer than 11.9 ounces. See how that works? But we can do better than that. We can use what's called the standard normal table. Okay, so there's a table in our textbook that actually takes a z-score and converts it into a percentile. So here's what we're going to do. We're going to take every can that of soda that's produced by this company, and we're going to give each can its z-score. How do we do it? Well, we just calculate z-scores above, right? We did 4. So you understand a z-score, right? You take the measured fill for the can, you subtract the mean, 12, and then you divide by the standard deviation, right? So every can has a z-score. If the can has a little more than average, it's got a positive z-score. If it has less than average, it has a negative z-score. If it has exactly 12 ounces, it has a z-score of 0. So if you do a z-score for every can, you get the standard normal. Okay, so this is the standard normal curve over here on the left. Okay, Z is the typical letter we use to stand for the standard normal. Okay, so in the standard normal, the mean is 0 and the standard deviation is 1. Okay, so the way it works here with the table is we're going to calculate a z-score for a can that has a fill of 11.9 ounces. Okay, so we're going to use the z-score formula. We go z equals x minus mu over sigma. Okay, so x here is 11.9 minus the mean of 12 divided by the standard deviation of 0.12. Okay, so if you put that in your calculator, that's going to be about negative 0.83. Okay, so where's negative 0.83? It's about right here. Do you see how this area is the same as this area right here? Okay, so what we're going to do now is we're going to go to the standard normal or the z-table, and we're going to figure out what percentile a can with 11.9 ounces is. Okay, so the way it works is we take the z-score for that 11.9 ounce can and we look it up in our table. Okay, so let's go to the table. Where's the table? It's in the textbook. Okay, so remember, with the textbook, you can find that on the Canvas site. So if you haven't been using it much, you might have kind of put it aside. But go ahead and open it up and go to table A at the back of the textbook. Here it is. Okay, so if you have the textbook open, it's on page 191 of our textbook. It's called the normal probability table. And the genius of this is you can use a single z-score to find a percentile. Okay, so how does it work? Well, first of all, let me just give you a second. If you want to pull up your book, go ahead and do that. I'll pause for a minute and let you get that open. If you haven't ever downloaded it, it's available on Canvas. Let me remind you guys of that. So if we go to our home page, on the home page it says textbook here. So you click on the textbook, and then we have it in the regular form, and then we have it in this more easy to access readable form here. So anyway, there's the book. So open that up and go to page 191. Okay, so how does it work? Well, we can see here on the page, on this picture here, if you have a negative z-score, you can take the z-score and use it to convert it into a percentile. Okay, so in this table, the percentiles, I'm sorry, the percentages are on the inside. The percentages, the proportions are on the inside. The z-scores are on the margins. Okay, so the margins here are the z-score. So what was our z-score? Our z-score for that can of for that beverage was negative 0.83. So what I'm going to do is I'm going to break that into two pieces. I'm going to break that into 0.8 and 0.03. Right? So 0.8 and 0.03. I'm breaking it in right at that first decimal place in the second decimal place. Okay, so the z-score is negative 0.83, and I'm breaking that into 0.8 and 0.03. Why? Well, this 0.8 tells me what row to go to. So this is the row. This indicates the row, and this indicates the column we're going to be in our table. You know how these lookup tables work, right? So we're going to have some row that we go down to, and then some column, and we're going to look to see where they intersect, right? So I'm going to go to the row Z equals 0.8. Let me scroll out just a little bit, zoom out here just a little bit. So yeah, actually I can do that on one page. So here's our Z. Where is Z equal to negative 0.8? Right here. You guys see this row? So this is the row that's relevant for us. Okay, then we're going to go to the relevant column. So the relevant column is 0.03. That's right here. Okay, so I'm going to go down in this column, and I'm going to see where that column intersects with the row. All right, so this is the relevant column. This is the relevant row. Do you see where they intersect? 0.2033, about 20%, which is what we guessed from our diagram, right? That's the percentage, okay? So it also tells us the percentile, right? That's the 20th percentile. Okay, so 0.2033. So what it's telling us is that this area here is 0.2033. So if that area is 0.2033, then what's this area over here? The same thing. So our guess was actually very close. But we don't need to guess anymore. We know the exact value. So what proportion of cans have a fill less than 11.9 ounces? Oh, about 20%, or 0.2033 of cans will have a fill of 11.9 ounces or fewer. And that's very useful if you're the quality control engineer or the manager for this process, right? You need to understand how your machines are working and what your production looks like. What do you guys think? Would you like to see that table again, or do you feel like that made sense pretty well? All right, so you don't actually have to use the table in this class at all. All right, so I've got some good news for you. If you didn't like using the table, you never have to use it again. Okay, so when we were designing the course, about half of us said, don't even put the table in. It's antiquated. People don't use it anymore. Just use software. The other half of us were like, well, they might see it in another stats class later on, or maybe like on a standardized exam. So let's go ahead and put it in. Just let them see it, and then that way they're aware of it, and then we'll move on, and we won't really use it very much. Okay, so that's kind of where we fell with this. The table, honestly, it's a little bit outdated slightly. Okay, but there still are stats classes out there that use it. So we just wanted to show you how it works. And this is actually the last time we'll use the table for this class. Unless you want to use a table, you can continue using it, it's fine. But instead of using the table, we're going to be switching over to software now. Okay, but anybody want to talk about the table more? Now I'm going to put the table away. I will never come back to this page again. Unless you ask me to, and I'm going to do everything with this distribution in GeoGebra. Polly's like, nope, I don't want to see that again. That's fine. Let's move over to GeoGebra then. Okay, so let's do the same thing, but faster and in a more accurate way. Okay, so we're going to do this in GeoGebra. So open up GeoGebra along with me. And here's what we're going to do. We're going to go to the distributions. So to do that, we're going to hit the toggle button, the three dots, and then we're going to go to probability calculator. What does that look like? The normal distribution. Okay, so there's actually a ton of different distributions here. There's the student, the chi-squared, the F, the exponential, etc. For our class, we're only going to do the first two. This is an intro stats class, right? So we don't go beyond the first two here. So we're going to go normal, and usually that's the one that just pops up by default. So you won't even have to click on that. But just in case it gets weird, just go to normal, and then if we're working with a standard z-score, then we'll have a 0, we'll have a 1, and then if we want to know the percent that's below, we'll do a left-sided, and then on the inside here, we put in the z-score, which was negative 0.83. Does this graph look familiar to you? It's this graph right here. Yeah, or this one right here. It's the same thing, except theirs is better because it's done with software, but it's the same picture. Okay. So what this is saying is that the percent of scores, in this case the z-scores, that are less than or equal to negative 0.83 is equal to, well, there's our number again, 0.2033. Look familiar? Yeah, it's the same number, right? Except this is actually is typically more accurate because the table, it's rounded to 2 decimal places with the z-score, but here we can put in any level of accuracy we want. So it's faster. We get a nice picture that's updates, and it's just so much better than using the z-score. Okay, I'm sorry, it's so much better than using that table. That said, if you do take more stats classes, it's pretty likely you'll see one of those z tables in there. So we just want you to be aware of it. It's another way of calculating these probabilities, okay? So there you go. Your choice. If you want to use that table, go ahead. But I recommend using GeoGebra for everything. Julia's got a great question. Will the mu and sigma always be 0 and 1? Yes, if you are in the standard normal distribution. That's kind of the definition of standard normal. If the mean is 0 and the standard deviation is 1, then you are in the standard normal. But not every normal is standard normal, right? Think about the distribution of heights. Is the average height 0? No, right? Or weights, okay? Is the average weight 0? No, okay? So, and, there's different normal distributions. So the distribution for height, right? What's the average height? Maybe 70 inches for males. So the middle of that distribution would be 70. What's the average weight for males? Is it 70? No, it's probably like 180 or something, right? So these distributions have different centers and they have different spreads. But if you're in the standard normal, then yes, the answer is it will always be 0 and 1. Does that answer your question, Julia? It's a great question. So let's get more comfortable here with using GeoGebra for doing these kind of percentile type problems. So we've already done it once in GeoGebra, but so the directions are here though. So if you forget, you can come in and read the directions here. We also have the videos that are on YouTube. So let me just remind you of that. So if you go to our YouTube channel for this course, we have a ton of videos. So for the technology videos, there's a playlist for GeoGebra here. And then so just to remind you of this, so for example, the normal probabilities. That's actually me. These are some of the videos I did. And so, it's me doing the same thing that we're about to do right over here. So anyway, if you forget, then you can go and watch those videos. Okay, so let's work through some of these. Determine the area under the standard normal curve. Okay, so there's normal and then there's standard normal. So what does standard normal mean? It means the mean is 0 and the sigma is 1. Okay. All right. So if z is negative 1.52, what percentage of the population has a z-score that's less than negative 1.52? Okay. So I'll do a couple of these and then then I'll go quiet and let you practice with these. Okay. So here's what I recommend doing. Use the idea of the inflection point. You'll just get better results. You'll get, just results that are more intuitive and, it just helps. Okay. It's like a sense check. So if it's the standard normal, then I know that the middle is 0. Okay. And then I know the inflection point is 1. So where's the inflection point? Maybe about right there. Okay, just, it doesn't have to be perfect, but that's pretty close, right? So there is negative 1. I went a distance of 1, right? That's the standard deviation to the left, and there's my negative 1. So where is negative 1.52? Well, it's another half standard deviation below that. So half standard deviation is about like that. So maybe there is negative 1.52. Okay, so again, I'm just eyeballing it. It's not, it doesn't have to be perfect, but it does give me a nice feel for that value. So then, next thing you want to do is get in the habit of shading the relevant region. Okay, on exams, I'll ask you to do this, and then to prove that you know what you're doing, you'll have to shade in various regions of the distribution. Okay, so what proportion of the distribution is below that value? You know, I'm guessing maybe about 10%, right? Does that make sense? So, great. Yeah, Laura's thinking the same. So great. So seems like it makes sense, right? But I don't want to guess. I want to get the exact value. And it's very easy to do that with GeoGebra. So here we go. We run over to GeoGebra. Let's kind of reset everything so we can tackle this from the beginning. We're going to go to toggle, 3 dots, probability calculator. Okay. And again, the default will typically be the normal distribution with sigma mu 0, sigma 1. So we want the area to the left of negative 1.52. Okay, so notice we get the same graph that we did over here, except it looks better. And what is that area? Okay, so again, z-scores and measured values in the distribution go inside the parentheses. The percentages, the proportions, the areas, they go on the outside. So what does that mean? 0.0643? That's about 6% of the distribution has a z-score that's less than negative 1.53, 1.52. Okay, so we go 0.0643. That makes sense. Let me jump down here to something that's related, but kind of the exact opposite. It's actually the percentile problem. Okay, so we want to find the value in the distribution that has an area of some value to its left or right. So let me do this one in the middle. What is the z-score that has an area of 0.41 to its right? Okay, so how does that work? Well, let's look at the inflection point. Okay, the inflection point is about right there. So that's going to be about 1, right? Because this is the standard normal. So we have 0 in the middle, then we go out a distance of 1 for the standard deviation. Okay, so if that's 1, let's leave that in there. Then we want the area to the right to be 0.41. Okay, so let's think about 0.5. Is it clear to everybody why if I cut this distribution right in half, I have 50% to the right and 50% to the left? That makes sense because of the symmetry. So if I cut it right in half, then I get 50-50. But I don't want 50, I want 0.41. Okay, so what value in the distribution has 0.41 to its right? Well, then we have to go a little bit to the right of 0, right? So how far over do we go? Well, again, just kind of eyeballing it here, just kind of guessing, approximating. If I shade that area, does that seem like it's about 41% of the distribution, more or less? I mean, it could be better, but it could be worse. Does that seem to make sense to you guys? So if that's 0.41, the value we're looking for is this value right here. That's the z-score. It's the mark there on the x-axis. Okay, so where would that be? Well, if 1 is about right here, then what's that value? I don't know, maybe 0.2. Okay, so I'm just kind of guessing here, but it's an educated guess of about 0.2. But we don't need to guess because we've got the software, or we have the table if you want to use the table. Okay, so my best guess would be it's about 0.2. But again, I don't need to guess. I've got software. So let's go over to the software and do this. So we're still in the standard normal, but now we want the area to the right. So I'm going to hit this right bracket, and it's reversed because earlier we were finding a z-score. I'm sorry, we had the z-score and we were finding the area. Now we have an area and we want to find the z-score. So again, z-scores go on the inside, area is on the outside. So in this case, I actually know the area. So the cool thing about GeoGebra is I can come over here, I can click on this and I can write in 0.4, 0.41. And do you see how I get the same graph that I drew over here? Of course, theirs is better, but it's the same thing. And what's the z-score? 0.2275. Yeah. So I guessed 0.2 and I was close, but this is much better, right? It's to the fourth decimal place. You can never guess the fourth decimal place, right? So 0.2275. Okay, so that was our guess, and this is the actual correct answer, 0.2275. So if your z-score is 0.2275, that means about 41% of the population is above you in that measurement, right? So if your height has a z-score of 0.2275, then about 41% of the population is taller than you. So you're taller than average, right? Okay, all right. So on these, we do want to graph a little bit. So what would the graph of that look like? Well, something like this. We would have 0 in the middle, and then I would plot an area here for 0.41, and then I would have my z-score there as 0.2275, something like that. Okay, so we still have 8 minutes, so I think we can still get some nice work done here. I want you guys to do these other 4 problems. Okay, so there's 6 problems here designed to help us get comfortable with GeoGebra in the standard normal curve, standard normal distribution. I've done 2 of them. I want you guys to do the other 4. Okay, if you want to go solo, I understand. It's it's Zoom class, and that might appeal to you to kind of be more working on your own. But I will go ahead and open up a breakout room. So if you'd like to jump in and talk about this with some other folks, feel free to do that. Okay. If you want to ask me, feel free to ask me. Okay. So I'll go quiet for about 3 minutes, 3-4 minutes, and then we'll spend the last 2-3 minutes of class talking about a couple of these. Okay. All right. Great. So at 12:47, we'll come back together. Okay, so we have a couple more minutes here. Can anybody help me out with some of these? Maybe to the right of z equals 2.13. Does anybody have that one? Let's zoom in here and use our inflection point a little bit. Inflection point always can help us get a nice sense of this. So we go 0, and then the inflection might be about right there, so that would be about 1. So 2.13 is another standard, a little bit more than a standard deviation out beyond 1. So if you're to the right of that, you're in, you're kind of out there far in the distribution. You're more than 2 standard deviations above average. In fact, just looking ahead a little bit, this 2 plus or minus 2 standard deviations from the mean is a good way of defining an unusual value. So if you're more than 2 standard deviations above average height, then you're pretty unusually tall, basically, would be the definite would be a way of interpreting that. Okay, so if we guess, we would say, well, it's a small percentage, right? But is it 2%? Is it 4%? Our eyes just can't really guess at that level of accuracy. But we don't need to guess, right? We've got our table, we have our software. So we go z equals 2.13. We shade that region, and then we run over to GeoGebra, and we're saying greater than. Remember, the area goes on the outside, the z-score goes on the inside. So here we know the z-score, it's 2.13. So we get the same picture, it's a small amount. How small? It's like 2%, right? So 0.0166. Okay, so the area to the right of that would be 0.166. Okay, let's do one more of these, and then we'll be out of time for the day. Did anybody get this one? What z-score has an area of 0.23 to the left? Anybody? So that would be 0. Inflection here is -1. So if I had to do negative 0.23, where would that be? Where is 23% of the distribution? I don't know, maybe about right there. Right? Does that look like about 23%? Kind of hard to know exactly, right? So where would that be? It looks like it's to the right of -0.1. Okay, so we draw that. Let's see here. Yes, Armand got it. It is -0.7388. Great, thank you, Armand. Perfect. So we're going to go z-score, right? I'm sorry, we don't know the z-score. That's what we're looking for. We know the area here is 0.23. What's wrong there? Well, I didn't switch it over to less than, right? So I got to redo that. So we go 0.23 now. And yeah, sure enough, we get -0.7388, which is making sense. It lines up with our graph over here. So we would say z equals -0.7388. Okay, so if your z-score for weight is -0.7388, that means you're at the 23rd percentile for weight. Okay, 23% of the population is lighter than you are, right? Does that make sense? Okay, so we're out of time here for today. We're right where we need to be. We're supposed to finish this section, so everything is looking good for us. Are there any questions as we break for the day? Exams, I don't actually have the exams yet. They're still in the process of scanning them and shipping them over to me, or emailing them to me. Hopefully I get them today. So if I get them, in the next day or two, there's a chance I'll have them on Friday. If it takes longer to get them back, and sometimes it does, then I'll have them by like Monday or so. But yeah, let's see. Was there a question in the chat? Let's see here. Can I show the last one? Which one, Killian? You're talking about this one up here, the 2.13. Here, let me just zoom out here. You can see all of them. Is that what you wanted to look at, Killian? All right, well, guys, have a good one. I'm gonna sign out here unless there's other. Oh yeah. If you want to stick around, we can do this one. So the yeah, let's see here. So that surrounds the middle 80%. Yeah. So if you want to stick around, I'll do this last one here. Killian's asking about it. If you want to take off, it's fine. we are done here. But yeah, let's go ahead and just a little extra here. So middle 80%. Why would we care about the middle 80%? Well, think about a metric like blood pressure, okay? Or like, some measurement like blood pressure. You don't want to have a really high blood pressure. That's bad. But you also don't really want to have like a super low blood pressure either, right? So if you're too far out in either direction, it's kind of like an unusual or an unhealthy value, right? So sometimes with these quantities, it's it's the middle part that is kind of like the normal part, right? The kind of the average or kind of where you want to be. So you can imagine where we would want to maybe define a region for healthy versus unhealthy, and it would be kind of in the middle of the distribution, right? So it's probably more complicated than that, but that's kind of the idea here. So if I want to have 80% in the middle, what are the standard deviations that I need to have? What are the z-scores? So I need a z-score here, and I need a z-score here. So there's an easy way and a hard way of doing this. The easy way is to use symmetry, okay? So I think you can tell that since 0 is in the middle, then one z-score is actually just the opposite of the other z-score. So the easy way is to use symmetry and only do the calculation once. So you get one z-score, and then you put a negative in front of it and you get the other z-score. Okay, so let's do that. Let's do it the easy way if we can. So how do we do that? Well, if 80% is in the middle, then 20% is out in the two tails. Well, the two tails are equal by symmetry, so I can cut that 20% into 10%. So in other words, I have 10% over here, and I have 10% down there. So what is the z-score that has 10% above it? Well, that's the kind of question we've been answering for the last 20 minutes, right? So I'm going to go over to GeoGebra and I'm going to say, well, what z-score has 10% above it? Okay, so remember the percent, the area, the proportion goes on the outside. The z-score goes on the inside. So I put the 0.1 on the outside, and then the z-score pops up over here, 1.2816. Okay, so 1.2186. Is that what I said? 2816. Okay. 1.2816. So by symmetry, on the left, it's going to be negative 1.2816. Does that make sense? So between a z-score of negative 1.2816 and a positive z-score of 1.2816, that's going to define the middle 80% of your population. Okay, so it might be, as long as somebody has a z-score for their blood pressure between negative 1.2816 and positive 1.2816, that would be perhaps considered a healthy blood pressure, kind of something like that, right? It's a little bit simplistic of an example, but it captures the principle of it, I think. Any questions about that? Does that make sense, Killian? Let's see. Then I got another text here from Julia. Yes, I do have office hours. I have to go right now, but I do have office hours on Monday and Wednesday. Does that work for you, Julia? I've got, let's see, when are my office hours on Monday and Wednesday? I've got time from 12 to 2:30 on Monday, Wednesday. Does that work? Yeah, okay, great. So here's what you should do. Shoot me an email like right now, just so I've got it in written down, and it just helps with the scheduling. Or tomorrow morning, and then after my class, my class tomorrow ends at 11:50. I'll walk back to my office. I'll open up my computer, and then we can meet in Zoom sometime after 12. Okay, great. All right. See you all later. Take care. See you on Thursday. Bye bye.